My name is Mukesh.
This is Shiva Shyam.
We are the 7th semester students going to discuss about series LCR circuit.
Yeah. The main objectives of this experiment is to study the frequency response of a series LCR circuit
and to find the resonant frequency, quality factor and the bandwidth of the series LCR circuit.
We need the apparatus resistance box, condenser box, that is the capacitor, and this is the inductor, and this is the function generator, and two multimeters and connecting wires. So before connecting the circuit, first we have to check whether the connecting wires are working properly or not. So for that, we have to switch on this multimeter and then keep it at the position this Wi-Fi symbol. So now we have to place this connecting wires at this position. Yes, here you can hear this sound. That it indicates that the this connecting wire is properly working. In the same way, you have to check for every connecting wire. This is the series LCR circuit diagram. Here you can see this turning coil is the inductor, and this is the parallel plates or capacitor, and this one is a resistor. This is a alternating current source, that is a function generator. Here V in, that is V input, the voltage input. So if you want to find the input voltage, then it should be connected across the function generator. In the same way, we have to find the output voltage across the resistor. So the multimeter should be connected across the resistor.
Before doing the experiment, we should know what is the theory behind the series LCR circuit. So let us discuss about the theory part. Now, what are the components of series LCR circuit? Inductor, capacitor, resistor. The first component is inductor. So let us discuss about inductor. So what is inductor? An inductor is an electrical component that is used in most power electrical circuit to store energy in the form of magnetic energy when electricity is supplied to it. That is, whenever electricity is supplied to an inductor, it converts that electrical energy to a magnetic field, which help the inductor to store temporary energy in it. This is a symbol of an inductor for a circuit diagram. The SI unit of inductor is Henry. Now, let us discuss what will happen when we connect the inductor to an AC circuit. In an AC circuit, the direction of the current will change with respect to time, which causes the change in magnetic flux in the inductor. But according to the Faraday's law, change in magnetic flux will induce EMF in the coil, which tends to oppose the change in the current. So this causes some resistance in the inductor. Now let us discuss what is inductive reactance. The opposition offered by the inductor in an AC circuit to flow of AC current is known as inductive reactance. It is represented as XL, measured in ohms. Similar to resistance, inductor will also produce some resistance because of the change in current. Mathematically, XL can be derived as XL is equal to 2 pi FL, where XL is the inductive reactance, L is the inductance, F is the frequency of AC source. In the right side of the video, there is a detailed derivation of how XL is equal to 2 pi FL. Please feel free to pause the video and go through it. The next component in the LCR circuit is capacitor. So, what is a capacitor? A capacitor is an electrical device that stores energy in the form of electrical charge. It consists of two electrical conductors that are separated at a distance. The space between the conductors may be filled by vacuum or with dielectric. The ability to store charge for a capacitor is known as capacitance. It is measured in Faraday, and the symbol which is used to represent capacitor is this one. Okay, now let us discuss what will happen when capacitor is connected to an AC source. Before that, we should know when will current flow happen in capacitor is connected to a circuit. Current flow will only happen in charging and discharging phase of a capacitor. That is, when an empty capacitor is connected to a source, there created a potential difference between source and a capacitor, which causes the current to flow to the capacitor. Similarly, a fully charged capacitor, if it is connected across the resistor or inductor, again potential difference occur, so it will cause the current flow from capacitor to the resistor or inductor. Now, once the capacitor is saturated, it blocks the current flow through in it. That's why capacitor blocks DC current. But in AC circuit, as the direction of current changes, the polarity of the capacitor also changes, which causes both charging and discharging with respect to AC current. The capacitor also offers a resistance in the electrical circuit. The resistance offered by the capacitor in the AC circuit is known as capacitive reactance. It is represented by Xc. Mathematically, Xc can be expressed as 1 by 2 pi Fc, where X is the capacitive reactance, C is the capacitance, and F is the frequency of AC source. Let us discuss about LCR resonance circuit. In the series LCR circuit, an inductor, a capacitor, and the resistor are connected in series with an AC source. When an external alternating current causes an oscillatory circuit to oscillate with maximum amplitude or generate maximum gain, an electrical circuit is said to be in resonance. The overall resistance offered in the circuit is termed as impedance. Mathematically, it can be calculated Z is equal to under root XL minus XC the whole square plus R square, where Z is impedance, XL is the inductive reactance, XC is the capacitive reactance, and R is the resistance offered by the resistor. The LCR circuit oscillates with maximum amplitude when circuit offers least resistance. So for this condition, the reactance of the circuit must be minimum. That is, XL minus XC the whole square is equal to 0, or else XL is equal to XC. This is the condition for resonance in the LCR circuit, which means when the inductive reactance and the capacitive reactance are equal, the overall resistance offered by the circuit is minimum, so that it will produce the maximum voltage gain or maximum amplitude which will offered by the LCR circuit. At this condition, the LCR circuit behaves like a purely resistive circuit. Why? Because if you substitute XL is equal to XC in the impedance formula, you will get Z is equal to R, which means the overall circuit is act as a purely resistive circuit. Further, if you substitute the formula of XL and XC in the equation, you will get 2 pi FL is equal to 2 pi FC. Upon further calculation, we get F is equal to 1 by 2 pi root LC, and F is called as natural frequency of the circuit. As you can see in the diagram, the maximum peak voltage which we can be calculated using the formula F is equal to 1 by 2 pi LC, where L is the inductor and C is the capacitor of the LCR circuit, and F naught is the natural frequency and A naught is the maximum voltage gain occurred in this LCR circuit. Further, we can calculate the bandwidth and the quality factor of the circuit. Bandwidth can be calculated by dividing the voltage by root 2, which will divide the graph into 2 points F1 and F2. Subtract those 2 points to get bandwidth. Dividing resonant frequency upon bandwidth results in quality factor. The more the quality factor, the more the efficiency that LCR produces the maximum amplitude. That's the end of the theory part. Now let us jump into the experiment part.
Okay, now the circuit is ready. This is our function generator. It has a frequency range from 1 Hz to the 3 million Hz. You can see that. And this frequency can be changed using this fine knob. Also, it has a function, that is value, sinusoidal wave, triangular wave, seesaw wave, etc. It has impedance and attenuation. It can be altered. And this frequency generator has two different channels. So we have used this channel for our experiment. Now let's start the experiment. Now the frequency is around 220. Now let's increase the frequency, and while you observe the output voltage and the input voltage in the multimeter. So when the frequency is being increased, you can observe the input voltage is falling down and the output voltage is increasing. Yes, still you can see that the output voltage is increasing and the input voltage is decreasing. Now, after reaching some point, we can observe that output voltage is decreasing and the input voltage is increasing. So, corresponding frequency at this point is called resonating frequency. Since it's a demonstration, we didn't take input voltage and output voltage values. But when you perform the experiment, you will observe a notable change when we cross our calculated resonating frequency. So this is the end for our procedure, and now we'll look into the observations part. Okay, now we'll see how to take the observations. So this is the tabular column. It has 6 different columns. In the first column, it is frequency. This is input voltage, output voltage, gain, that is voltage gain, that is a ratio between output voltage and input voltage, inductive reactance and capacitive reactance. While performing the experiment, we have chosen a range of frequencies in such a way that our natural frequency was in middle of that. So suppose we got a natural frequency at 800 Hz. So we have chosen the frequency from 300 Hz and to in and around 1600 Hz. So for every interval of 50 Hz frequency, suppose if you take 300 Hz, note down the input voltage and output voltage. So for that you can calculate the ratio between output voltage and input voltage. So you will get voltage gain, and we can calculate the value of inductive reactance and capacitive reactance by simply substituting the values of F, L and Fc. And while performing the experiment, we have observed that at 300 Hz the input voltage was 5.68 and the output voltage was 4.28. And after the 50 Hz, that is 350 Hz, we observed that input voltage was 5.55 and output voltage was 4.46. So in this way, you note down the readings for input voltage and output voltage of different frequencies. Now, so in this way, for every 50 Hz, that is up to 1600 Hz, you take down the readings of input voltage and output voltage, and then you calculate the values of voltage gain and XL and XC for each corresponding frequency. Now, you plot a graph between voltage gain and the frequency. You will observe that a bell curve will be forming. This peak value is A0, that is maximum voltage gain. This will be attained at the frequency of natural frequency. So the which is also said to be as resonant frequency, means when the circuit has attained the maximum voltage gain, then that frequency is said to be a resonant frequency. So theoretically we will say it as natural frequency, and experimentally we will say it as resonant frequency. Now, if you take the value of A0 by root 2 and if you draw a parallel line parallel to the x-axis, then this line will intersect the curve at these 2 points. So the corresponding frequencies at these 2 points is F1 and F2. So these two frequencies are said to be lower bandwidth, lower frequency and higher frequency of bandwidth. So if you subtract F2 and F1, we will get the bandwidth of the LCR circuit. Now we have another important factor to be determined, that is quality factor. Quality factor is the ratio between the F0, that is resonant frequency, and the bandwidth. Now, what is quality factor? Quality factor means it will give the value, it will give how well the circuit is performing. So if the quality factor is good, then we can say that the circuit can store more energy. Now, in this way, we can calculate the value of quality factor. We know bandwidth from the previous part, and F0 is a resonant frequency. There is another important factor to be determined, that is called quality factor. So what is quality factor? Quality factor is it is a term that will tell whether the circuit is performing well or not. If the quality factor is more, then the circuit will be storing more energy, and also the bandwidth will be very narrow. So it has a formula, that is F0 by bandwidth. F0 is the frequency at which maximum voltage gain is observed, and bandwidth we have seen in the previous part, that is F2 minus F1. Now, that is higher frequency minus lower frequency. Now we have another graph to be plotted, that is it is XL or XC versus frequency. XL or XC is that is reactance. Now here you can see a curved graph and a straight line graph. This curved graph belongs to the inductive reactance versus the frequency, and the straight line graph is for capacitive reactance and the frequency. So the point at which these two curves are meeting is called at this point the XL value and XC is equal. So and the corresponding frequencies are resonating frequency. By plotting the graphs between reactance and frequency and voltage gain versus frequency, we can study the frequency response of a series LCR circuit.
And also by substituting the formulas, and we can find the natural frequency, and also we can find the maximum voltage gain corresponding to the natural frequency, etc.
Yeah. Also we can by using the formulas we can calculate the quality factor and the bandwidth.
Yes. We came across many procedure of series LCR circuit. Let us see what are the significance of series LCR circuit. Series LCR circuit are used in radios that we are listening, and we are using induction, which is based on the principle of series LCR circuit, and the last one is voltage multiplier used in major industries, which is also based on the principle of series LCR circuit. With that, we conclude our experiment. And this is me, Mukesh, signing off from here, and he. Sure, sir. Bye.